of Texas A&M at Commerce. I've known Kiki for quite a long time, and he has quite an impressive biography from PhD of Purdue of 2003, research assistant at CERIAS, then to the industry, chief scientific officer, I think, at one of the companies, and now to an assistant professor at Texas A&M. I'm sure I forgot quite a few things about Kiki, but he will be happy to talk about his research and himself. Kiki?
Thanks. Not about myself. It's not at all about myself. If anything, it's about the research lab, the Ontological Semantic Technology Research Lab that I represent at that university that I was happy to recently found with a bunch of colleagues after starting there, and that we're hoping to turn into a hub of expertise in our little corner in Northeast Texas, connecting to the whole country, including Purdue, with people working here, but mainly for the area of Texas for ontological research. And what I want to talk about today are two of the projects. One, a pilot, a little older. The other, quite the opposite, something that's in progress and the results are yet to come. And these are projects of that research lab and are united by my interest as a linguist in ontologies for natural language processing. First one is on a new baseline, a semantic baseline spam filter that we recently created a pilot for. And the main assumptions for this one were that most spam is, or at this point was, meaningless, because spam mimics natural language text, but badly so. But it does it to, of course, pass spam filters that people create, and also keep human interest enough so that they click the link that will take them where they actually don't want to go, and where harm waits for them. And the hardest thing about natural language to mimic is its meaning, the intangible thing that lies behind language, and that it is all about the thing that we use it for, namely to transmit meaning among us. And if you don't put work into mimicking your language, then its meaning will be very faulty, and that is where this method tries to take advantage of the laziness of the spammers. So spam is mostly, at least in the past, word salad. At best, it may be syntactically correct, so at first glance, your sentence does look like an English sentence. And we will look at colorless green ideas that sleep furiously. I already promised that to you. I know you were waiting for that. So this is old school spam. That's dreck, right? It doesn't even look like a language, except that it uses words and points you to what it wants to sell you. And this one is a real-life example from a blog where a humor topic of mine was discussed, and I had subscribed to it because I wanted to see what people were commenting on. And 90% of what was posted after about week one was this kind of spam, right? So this is what you get, people trying to sell you virtual currencies for their online games. If you're ever unemployed, you can go on WoW and start farming for WoW gold, and then spam blog posts and sell it. Sometimes you get things that are syntactically a little better formed, like this one here, where people were harvesting real natural language text, either other blog posts or emails or whatever, and then haphazardly injecting the keywords that they were trying to make people get interested in. And what's more common these days is that people do it somewhat intelligently. They harvest a piece of text somewhere, they parse it syntactically, and they say, I identified where nouns are in this text, and my vector noun that will take you to my bad site, I will put in the place of an actual noun in the real text. So that looks like real language at first glance. But it is definitely semantically ill-formed, because I don't even know what Fiesta Gold is. The language model that we applied for this is based on meaning density. Our technology parses text semantically and represents its meaning. So you take a piece of English, we parse it, take the meaning of it, and represent it in a fully formal language that is not English, but that captures what we think is important about its meaning. And with this in mind, the main assumption about the concept of meaning density is if a text has little or no meaning, like the wow gold you saw, then our technology that tries to find the meaning of it will produce a very small or actually no representation of the meaning of that text because it has no meaning. We're going at the text with our parsing technology like a human does, try to get the meaning out of it. If for a human text has no meaning, then our technology should present no meaning coming out of it. So if spam has little or no meaning, as it used to and often still does, then our technology should produce suspiciously small pieces of representation of meaning, or actually none. So if I take a human text written with the purpose of representing meaning, our technology parses it, we get a rich representation of the actual meaning of the text. If I throw gibberish at it, our technology parses it, it should not produce any meaning because it can't. It tries to find, as humans do, main events in the text, the participants in these events, etc. We'll look at that in a little more detail. So, if text like that produces no TMRs, it might be spam. That's the simple assumption. And as we will see, it might have been a little too simple overall. But let me give you a quick introduction, if you haven't heard it 8 times already, about how this technology works. Ontological semantic technology uses expert-created knowledge resources about language in general and about the languages that you want to parse in specific. And in our case, it's English. So if you throw texts at it, we have some collection of algorithms that parse the text, and they start like the usual stuff that you know. They tokenize, they have lexicons in which they look things up after stemming. But our lexicons are a little different than other lexicons. They try to actually capture the senses of every word. And it may be news to you, but most words of all languages have more than one meaning. That being one of the big processing obstacles, namely ambiguity. So how do we get the ambiguity out? What are the resources that we use? For one, as I said, specialized rules, morphology, and so on for every language, for stemming and those common things. Lexicons for each language, representing for each word all its meanings in terms of concepts that I'll talk about in a moment. But you also need proper name databases. Named entities are a big thing in text that don't really belong in the lexicons of the language, but they are language independent things that have special interest to most applications of natural language processing. But at the core of this whole endeavor is what we call an ontology. And you can think about it simply as a database that captures the things and events that exist in the world and all their relations among them. And then if you want to express the meaning of a sense of an English word, you point into the ontology where the required concept resides, and then you not only know that this concept represents the meaning of a word of that language, but you know all the relations that this concept has throughout that database, and all that relations may be to yet other concepts for which there are words in the same language that you are processing in the very text. So you can discover the relations between the concepts of a text as they are evoked by the text in relation to a general database that tells you how the world works. It spits out a representation of the meaning of that piece of text you threw at it, of which we will see an example in a moment. And you can use that representation of meaning for all kinds of things, all kinds of really clever things, actually, much more interesting than spam filtering. But as you go along developing such a system, it may not yet be very robust, and its output may be sometimes very funny still. And that's why we came up with the concept of meaning density. We process text, we produce output, and it may still be somewhat funny, but at least we produce output. But if we can't produce output because the input text itself was somewhat funny, then something was wrong at that end already. That's the main concept here. We can store what we processed for future processing, of course. When I process one sentence, as in every human text, the next sentence may refer back to it. You may need that. Or if I process one text, I may later process another text that talks about the same event. You may want to compare between the two for possibly identifying that one text was lying. Here, it's very simple, just meaning density. Okay, here is a sentence that we threw at our program that produced pretty high meaning density output. The orthopedist reviewed the radiogram of the patient's neck. This is the output. The text meaning representations, TMR stands for that we produce, are anchored in main events. So we try to identify main events in the input text and then relate all other things that we can find in there to those main events. As I said, words in English, as in other languages, usually have more than one meaning. So we will definitely find more than one event, even if there's just a single event carrying word in there. But for a given sentence, you identify dozens and dozens of events commonly. What we then do is we identify the other participants in the sentence, their potential senses, and we try to match them up. So I take one candidate event here. What ended up being the top one is checking info as a sense of review. And we see if all the other words in the sentence have senses that jive with reviewing info. Then we create a candidate text meaning representation, set it alongside all the other candidates, and then say which one has the best match of all participants in this proposition structure here. And that's the weight you see at the top. This one came out at the top. And what this thing says is we took the word review, we identified it as having at least one verbal sense, V1 there, and that verbal sense in the English lexicon mapped into our ontology onto the concept check info. So we instantiated that concept, gave it a unique handle 1, because we may have more than one review info event in our text. And we found for orthopedist, which we know from our lexicon has at least a noun sense, that it is a doctor. And all the information after doctor that you see comes from the ontology. It's a doctor who does something, namely treat conditions. And the type of condition in particular that that doctor, the orthopedist, treats is a musculoskeletal disease. All of this comes from the ontology. We furthermore found a sense for radiogram, which is a picture that's the output of x-raying something. And from the ontology, again, we know that pictures can have topics, like any information object can represent something. And again, here we found that neck, that is part of patient, could be the topic of that picture. So this is one arrangement that our software produced that makes sense of all the words in the sentence, maps them onto a concept, and the concept dance that we see there is one that we expected. These concepts match each other in a way that our ontology likes, gives a high rating as a good match. So what this says is something like there was a check info event. It was done by a doctor who habitually treats a certain type of disease, namely musculoskeletal diseases. What he checked the info of is a picture that was produced by an X-ray, and that has the information content of a neck of another human who has a patient role. That's pretty good representation, and a pretty lucky hit that we had there, where this really is, I think, what we would agree, what most humans take away from that sentence. Our software often produces, as I said, very funny things that do not look that good at all. But high information density, and how did we quantify that? We said this has 10 input tokens. 5 of these contributed to the TMR, so we said meaning density of 0.5. That's one way you can quantify it. There's a bunch of other ways you could think of. But what you have to keep in mind that between language and the meaning of language, there's definitely no one-to-one relationship. You often have a whole bunch of words that just are used to evoke one concept, whereas on the other hand, you often have just one word that evokes a bunch of concepts. So if you look here at orthopedist, that word contributed at least the concepts doctor, treat condition, and musculoskeletal disease to our TMR. So that could be somewhat idiosyncratic relating to how our ontology is built. We could have had a shortcut there that just mapped the English word orthopedist to a child concept of doctor, orthopedist, and then it would have only contributed one concept to the TMR. So the quantification is not completely objective, but as I said, expert-generated intersubjective. And the famous inverse example, when I say kick the bucket, I do not invoke the concepts of kicking or a bucket in my hearer's head, but it's just about dying, right? So we have a ratio of at least 2 input tokens if I take the stop word the out to one concept there. And that's indeed what we did. We always ignored stop words because there could be many of them that destroy our beautiful meaning density ratio that we wanted. But as you see, orthopedist and radiogram evoked more than one concept. So it's not one-to-one, and that might be a problem for our measure, of course. But let's look how it performed in this very simple version that we used. Who has not heard this sentence? I'm glad that linguistics has some effect on the greater population in that one famous linguist came up with a sentence that is a perfectly good sentence of English, but when we try to make sense of it, its meaning, it just doesn't jive, right? So this is classic nonsense. Colorless green ideas sleep furiously. Chomsky's example of a syntactically grammatical sentence whose semantics just does not work. Indeed, our technology was unable to parse the sentence. I know, I make it very easy for myself to succeed. We have 5 input tokens. 0 of them contributed to the text meaning representation. That was the output. Meaning density 0.0, likely spam candidate. Very good. What's wrong with this sentence? Well, for one, ideas can't sleep, right? In our ontology, somewhere it is captured that the agents of any sleeping type event must be animate. Unless we want to talk about metaphors, which we don't, because as soon as we allow metaphors into our text processing system, we open the floodgates for science fiction, fairy tales, and all of that to work. And poetry, even worse, yeah. We don't want that. We don't want ideas to be able to sleep. So you're saying Chomsky was a poet when he wrote this sentence, right? Ideas can't have colors. Ideas are a certain type of object that is not physical objects. They're mental objects, and only physical objects in our ontology can have colors. So the domain of the property color is physical objects, unless again you suffer from synesthesia and all of these beautiful things. But
Or things which are sort of given some value, we can talk about here. many people will understand that that's communist ideas, but that's a different kind of red.
Or Republican these days.
Yeah, red states. That's very counterintuitive for anyone who has from communist black countries.
Yes.
Yep. Yep. So for now, if we allowed our system to process these things successfully, our system would produce bona fide text very badly. So pushing it aside. So ideas for us can't have colors because only physical objects can't have colors. But there's other things wrong with this sentence that our technology in its current state didn't even pick up on. Ideas can't at the same time have the color green and have no color. For us humans, that's a matter of course. But to teach that to a computer, that one property can only have one filler, is very costly because there can be properties that have multiple fillers. If I think of the property is wearing clothes, which is probably a bad property, but I would want to allow multiple fillers for it. Otherwise, only people in onesies could be processed successfully, right? But my property of wears clothes at least has for you two visible items. And as any presenter at conferences, I wear no pants. Sleeping can't be done furiously. We're not capturing that. To humans again, that is very clear that that can't be done, except that if I ask a native speaker, you will immediately create a context of nightmares and so on, and tossing and turning and all of that. So Chomsky was a poet. Yes, you all want to tell me the sentence makes sense, it's poetry. But as an example, however concocted, it is semantically malformed, and our software failed on it as we hoped it would. Let's look at a few more in-between examples.
It succeeded by failing.
Right. Namely actual spam types that we used for the pilot study. Simple one, non-English spam. We don't have a dictionary for this language, which I'm not sure looks like Japanese to me.
No Japanese.
It's Japanese.
Okay, thank you. Well, with Dolce and Gabbana in there, which would be used in that same way because Japanese uses brand names and spells them out with the English lettering for it. But we were unable to build a text meaning representation for this because, of course, even our tokenizer failed on this. Probably spam. Keyword spam. This one really is just throwing out words that are, I think in this case, intended to attract human attention, not so much to confuse spam filters. As you know, you can throw in there words with low overall frequency in texts, and then spam filters will set their scores wrong. So if I speak of serendipity in my keyword spam text, I have a good chance of confusing some old school spam filters. That's not what's going on here. It's just stylish design, etc., etc. And our meaning density here was 0.32. So we were able to create some TMRs from this, but as few concepts were created as we were hoping for. If we look at tougher types of spam, syntactically correct spam, where someone actually created a sentence in which wow gold or whatever made sense, we get, sadly, good meaning density, almost normal language level density. And for the pilot, we set the threshold at 0.4, and this was above our threshold, so this would have gone through. This would have ended up in your inbox, I'm afraid. Sorry. So, as I said, we set the threshold at 0.4 meaning density. We used 245, really just pilot-sized block comments. And it was highly skewed towards spam, and that, of course, had a negative effect on the evaluation. But this is real life. This was my beautiful little article about the laughter epidemic in Tanzania that somebody wrote for a radio station. 9 people said, oh, this is interesting research. 236 said, wow, gold, Ed Hardy, Dolce et Gabbana. This is what happens when you don't have someone cleans up those beautiful blog comments. With our method of 9 ham, only 1 was misclassified as spam, so only 1 got through, so to speak. And of 236 spam, 11 were misclassified as ham, so these are bad, spammy messages that our method led through and said they could be real text. So we have a real low precision. That might be bad, but I think for this type of system, this could present a baseline for semantic spam filtering, but I'll say a few more words during the outlook. But overall, let me sell it to you a little more. A human editor would only have had to delete 11 spam messages, and only 1 beautiful comment about how interesting my research topic was would have gotten lost. So maybe for this application, the low precision is acceptable, but it is a pilot study, it is skewed. I could never even submit it without being kicked out of the room at this level, but it is a proof of concept for the technology. So what I'm claiming is even the simplistic baseline meaning density produces some results, although the corpus was small, it was biased, but combined with existing methods that would get rid of the other obvious types of spam, of keyword spam, we would reach a real high performance of precision and recall. So that is where I intend to take this next. Complementarily combine this with existing keyword spam filters, but even more importantly, and that is what I would prefer to do, but it depends on the further maturing of our ontological semantic technology, I would want to create real semantic spam filters, and that just not go in there and say, I create some ratio of what I could process versus what I couldn't process, and then we throw away what I couldn't process, but that goes in and says, I process the language, I represent its meaning, and in a certain AI-typical metaphorical sense, I understand it. And I say, this is spam because, like a human would read it and identify it as spam, I have criteria, and I say this is spam because, for example, I identify concept outliers, and the idea for this method that we'll work on is that well-formed text, we would assume, usually has a circumscribed semantic footprint. It will evoke concepts of one area in my ontology. It will talk about sort of related things throughout, and it's a dangerous assumption, of course. And it may have one or more of those concept footprints. So I send an email to a friend, I talk about soccer a little bit, then I talk about the new job I got, but I talk about soccer with a bunch of related words pointing to related concepts, talk about my new job with a bunch of words that evoke related concepts. But then if in there is a conspicuous outlier that does not fall within either of the footprints, that might be a flag for spam. It might also be a flag for something else, namely that I'm a jokester. And this wouldn't really be text understanding, because I should use outliers of a specific kind. So apart from that footprint, you would want to have a set of target concepts that your outliers should be. And obviously it would be words that evoke prescription drugs and things like that, and online currency, as we saw on the previous things. So that would be a better method. Rather than just fishing out keywords that relate to these, I would at the same time be able to say these words that evoked the suspicious concepts are outliers that don't have anything to do with the rest of what the text is about. Music of the future, as we say in German, but an interesting project that we're going to be working on next. But until we get to this, I want to introduce to you another project that we're currently working on at the OST lab, and that we're actively working on. So we might have other results there, and definitely will have results sooner. And the idea here is that we replied to a call for papers, call for proposals for automatic threat detection. And we have in our group an expert on image recognition and object and image recognition. And at the same time, we have the ontological expertise on campus. And we came up with an interesting combination of these two types of expertise to address this call for automatic threat detection proposals. The idea is in an image, moving or not. Moving has, of course, additional problems. So let's assume not in the moving image for now. An assault or automatic weapon is detected. Then automatically an alert should be sent out to a competent team that should reply to such a scenario, which we would want to distinguish from just a normal semi-automatic pistol, dangerous enough, being detected, that maybe the police can take care of. And if you think of variations of these scenarios, maybe you have several groups of perpetrators entering a public space, and you are automatically able to say this group poses more of a threat because of the weapons or weapon types, and this distinction will become important later, that they carry, versus this other group who just have ice picks and are, of course, after Trotsky again, and you only have one SWAT team. You would want to send it to the people with the automatic rifles, right? So here is the scenario, and we want to address it in an interesting fashion where our expertise converges to bring up a new ability for automatic weapon detection. So what we need to do is identify and recognize firearms. Just saying that a gun is there is nice, but we actually want to know what type of gun. It operates with an image of the situation we're looking at, so camera footage. And again, I'm excluding issues like how do I track the same gun from image to image and say this is one gun across several images versus these are two guns that first this guy has the one, then that other guy has another, and the first scenario would have been one gun handed on. This is all important stuff that we'll have in the second phase of this project. But the idea is low-level visual features help us in general identify what probable gun or gun type it is, but then we use the high-level semantic features of an ontology of these guns to assess the threat of these guns, dependent on parameters like its use in the given space. For example, it's really stupid to carry a hunting rifle into an enclosed space and try to kill people with it. That's why I'm saying it to you, because I hope when you go mad you try that. But it's better to have something with a shorter barrel and a higher rate of fire and a spread of ammunition and things like that. So these are features of the guns and their capabilities that we would take from the ontology after we have identified the gun visually and then combine them to assess the threat of a given situation. And I know it's a very macabre situation, especially given recent events, and that was one of the guiding impetuses that made us want to prevent things like that with our shared expertise here. So one problem there is how to quickly generate a visual footprint of a gun that helps us do a lookup in our ontology of gun images, and I'm not the expert on that, but I'll briefly introduce it. So how can geometric feature processing methods identify and recognize guns? But then how can the high-level semantic information facilitate the identification of guns or gun types when you're not sure which gun it is? And the idea here is I may not be able to tell you exactly what maker and model your gun is, but from its visual footprint, I have in my ontology an intermediate node that says, for example, assault rifle. And I can say with high probability, I don't know what your gun is, but it looks like an assault rifle, and I can give it the combined threat score of assault rifles. So I don't have to have a full hit on your gun, but from clustering all the visual footprints of guns, I derived intermediate concepts that should hopefully coincide with intermediate ontological concepts, and that helps me assess the threat of non-terminal node guns. So think about it as I'm really stupid, I'm a computer, and all I have is hierarchies of images of guns. These should cluster, and they do, because gun types from their outline represent relatively well what type they are, which relates to threats. But these automatically derived clustering nodes, we need to assign a threat score to, and that is, again, an expert-created number. So what we end up with ultimately is we have one hierarchy of gun images with intermediate nodes through clustering of the visual images. We have another hierarchy of guns as an expert has put them into the categories that they belong to. For example, commonly semi-automatic pistols, assault rifles, hunting rifles. There's special types of rifles like sniper rifles and so on. And these terms I just told you are intermediate concepts again, under which you have actual guns as their terminals. And the problem for our method is we want to converge the intermediate nodes from automatic image clustering with the intermediate nodes that an expert said are classes of guns. So that if I find a gun visually, I don't know exactly which one it is, I can trace it to its first intermediate node, and I hopefully have on the concept side an intermediate node, namely a class of gun, that will tell me this is the threat level of that gun. That's all I already said. Here is the ontological semantic concept of one of the guns. Fittingly, it's the AR-15 that was used in recent events with the relevant parameters that contribute to its threat. Not least things like rate of fire, muzzle velocity, caliber, but also things like overall length, which relates to how easily it is concealed and carried, things like weight with the same effects for how you carry it around and how not. So this is one terminal node in the ontological semantic gun ontology, and this is
What is rifling?
rifling. Almost all current guns have rifling. It's the spiraling grooves in the barrel that spin the bullet, so it has more stability in its trajectory. Yeah, there's very few guns that don't have that, but it makes a big difference for the range of the gun. Here is the overall ontology for you, just your usual hierarchy, because you can't see what the labels here are. But in this one, we only have guns, and since I can't move from my station here and point at things, what you would see here is that we have distinguished from expert input personal firearms from crew service firearms. There's guns that require more than 2 people. And the expert source we used is Jane's Infantry Arms Manual, which is kind of the industry standard for these things. Among the personal firearms, you find anti-materiel rifles, automatic personal firearms, handguns, and long guns, and then further down and down and down with presumed different threat levels assigned to them. So this is the expert-generated, what we call high-level conceptual ontology, and this is to the degree that I can recapitulate it, the visual footprint that we create of guns, And I'm not the mathematician on the team. Probably there are more mathematicians in the room. But the general methodology is creating convex hulls of those guns with, again, all the beautiful problems that you run into, because terrorists usually aren't carrying their guns like this for you, for the camera, but they are, of course, tilted in all kinds of ways, and they're usually partially concealed. So apart from these convex hulls, which we use for clustering of the visual images of the guns, we have a finer level representation of the firearms with their individual pieces. So if we can't do a quick recognition based on the convex hull, and if we can, then we can just look at the children of that convex hull intermediate cluster. If we can't do that, we do a costly, slow search of lower level visual images of the guns and their individual features. And this is one of the clustering algorithms that we used that led to these intermediate concepts represented by the empty circles that just emerged from the type of clustering algorithm. And onto these intermediate concepts, we hope to be able to map the weapon class concepts from the conceptual ontology. And it looks like using different clustering algorithms. Here is a different one that we used. We have some non-obvious overlap between the visual hierarchies and the conceptual hierarchies. And in this one, the length of the line to the connecting point indicates how similar this gun is, how well of a representative of the artificially generated subclass. And the basic algorithm type is just tree matching, like a variant of edit distance that we will be using for this. And that is, apart from questions, what I wanted to talk to you about in terms of what our lab does for security of information, but also security of people from guns. Thank you. No math questions.
It's not a math question. I was wondering about your spam software and its error rate on different types of font and maybe like typography, maybe kerning. If there is a space between each letter, is there an error rate? Is it able to detect everything?
It's too stupid for that. It only operates on non-image text. What you are referring to is a more recent method where people are sending around images containing the information, which you could OCR and then submit to our software, but we haven't done anything like that. And it lies outside of the domain in which the software wants to operate. It wants to operate with language to meaning. And then yours is more operating at the level of different representations of language as to standard representations of language and suspicion in that kind of thing. Does that make sense?
There was also, when Michael and I in the research group which first quoted ontological semantics into security matters early in the 2000s, and Peter was one of the members of that. We looked at steganography, and there was a strand of research into proportional spacing, manipulating proportional spacing, differentiating it, and thus building in a message. So there was some attention to what you are talking about there. I don't think there was anything manipulating the fonts, but OCR removed slightly different results, so it was lost. Please.
Yeah, when you're done with this, I've got a completely different question. Okay. Yeah, I think your results are actually a lot better than you realize. And that is because what you chose as a test bed was not email spam.
Mm-hmm.
It's web spam. And the purpose of that web spam is not to get someone looking at that blog to click on those links. Everybody, they know nobody looking at those blogs is going to click on those links.
Mm-hmm.
The goal is to get when you search for those keywords, they want the search engines to think, oh, your website is what everybody points to when they have those keywords.
Okay.
So the target of this is actually the search engines who are trying to prevent people. They don't care if they have a couple of false positives, because all a false positive means is, well, maybe we should have used this in increasing somebody's rank. They care about, and even a few false negatives are okay as long as you get most of them. So if you take your particular example and look at it in light of who really wants it, it's the web search engine companies, and I think you'd find those results are pretty good.
Okay, yeah, no, true. I hadn't looked at it from that angle, but it makes sense. It's a compound document. We're not looking at the individual responses as target, but what happens to the overall document.
I think if you look at some of the papers in web spam, that's really what you should be comparing with, and I really don't know what the
Numbers.
state of the art is in that area, but
Yeah, no, thanks.
I think
That's
you may
good.
find that you actually look pretty good there.
Okay, thanks. I hope so. I'll definitely use it as a pointer. Mike?
So, there's always an arms race between.
Please use your microphone while you ask the question.
Sorry. So, there's always an arms race between, like the virus and antivirus writers, and this too is an arms race. So, suppose I'm a bad guy, and I've read your paper, and I'm aware of the techniques you use. What's to stop me from using them for my purpose? That is, use exactly those semantic technologies for the generation of spam. If you get desperate enough, you could do that yourself, actually. But I don't see any difficulty in actually using this in the reverse direction of the generation of spam.
It is a backup plan, but luckily there is a barrier of entry to that, because natural language generation in principle is harder than analysis, because you're going from the abstracted unit, the meaning representation, and then you want to generate surface natural language text that is palatable to humans. You have to make a lot of choices of which synonym do I use, is it an active passive sentence, and so on. All of these choices were made in the encoding, so if you throw language for analysis at the machine, it can expect things and operate on them, but it can't reverse expect things. At least it's much tougher for a language generation machine to know what choices to make in the actual encoding of surface language. So it could use templates or text snippets, but the full generation of a good natural language text is...
This is very interesting. This raises an important question. That are there technologies in I know there is some, but is there a notion of like a one-wayness, like a one-way computation or one-way function that you can do it in one direction, but not in the other?
Well,
I don't think so. I had a funny experience, political more than anything else. Back in 1981, 89, I was invited to participate at the Alabama Symposium on Promise and Peril of Computers. It's an annual thing in Alabama, and all the high school teachers of the state be present there, and invited speakers. One invited speaker was very famous, very leftist, pretty radical sociologist from New York by the name of Stan Aronowitz. And he was talking about the computer as being just the new means of oppression, capitalist oppression of the masses. So I grew up in the Soviet Union. I am not very susceptible to propaganda from either direction. So I said, I asked him very friendly fashion, Stan, off the top of your head, can you mention any object, technique, methodology that cannot be used to oppress the masses? And he said, most certainly not. So I don't know. It's a great idea to look into, something that you cannot reverse for bad purposes.
I actually was thinking specifically of ambiguity, because, for example, automated disambiguation is a well-known difficult question. Yet we humans are unbelievably good at disambiguating.
I'm looking for a Turing test.
Yeah.
I'm looking for something like that, yeah, yeah. I mean, I'm thinking, well, like, he could get funding for, or start a facet of this project that would consist of making it harder to misuse the techniques for an evil purpose.
Even without the techniques, though, one of the previous talks here, for those who are new to ontological semantics, was on phishing by Professors Sparker, Taylor, and myself last year. I don't know whether you guys have been looking at phishing. It's getting better by the day, by the week, by the month. That is, you get messages, and that's not in response to any techniques. It's just a self-regulating process. There are messages now that I, as a human, cannot tell whether it's an inept conference announcement or whether it is a phishing attempt. And that is a serious problem because we can only build computational systems to model our ability. If I don't have the ability, what do I do? And that's not in response to any technology. But you are absolutely right, it can be developed in response to technologies.
I mean, when you submit this, you should definitely discuss that not only it raises the bar, but you have to think of what will the adversary do when they read your paper, understand it, and change their behavior accordingly. And, the spammers will do that for sure.
So guys, there are 4 ontological semanticists here in the room. Every paper we write now should have a disclaimer, not for terrorists.
Well, a lot of the things you see assume that, here we raise the bar, this does better than all previous ones, but again, it assumes a static situation that, sure, it raises the bar, but what about after they read your stuff and react to it? And that's what you don't find enough of in the,
We
have a paper on the NP for that
You do?
You do?
with Boegi and Marat.
Oh, okay.
Basically, what happens and what can you do. It turns out that, so assuming you're using some sort of a learning technique, and essentially what you have to do is you have to change the change the attributes you're using in a way that it becomes very expensive for them to work that out.
So randomization.
Not
No?
necessarily randomization.
Yeah,
It's
yeah.
different.
I was just wondering about, so now the new thing is text messages that have spam. What are your plans for that, like for mobile phone spam?
In principle, nothing new because it's the same type of input that I take, natural language, conveniently not as an image, hopefully, and I should be able to use the same techniques, with the proviso that they might be so short that I get a lot of trouble from not being able to process them, because the input does not allow me to create semantic dependencies with which I can decide, oh, this is human level meaning carrying text, or this is just gibberish. So it might just get harder from that. Am I emceeing myself? Are there further questions?